So I won't talk about the quiz that you've just done. I'll leave it till Wednesday. I'll put out probably a short page of solutions out onto the website, just so you can find out where or why you didn't. You might not have got full marks if you didn't get full marks. I don't think I actually set the thing to tell you how much what your score is. I'll flip that around, so hopefully you should see your results. In general, it was pretty well done. But as I said, the idea of these quizzes is to keep you on track, to make sure that you understand what's gone through the lectures. So in general, I don't want to be seeing questions about the quiz on the forums. You can ask general questions on the forums or on email, but please try and keep the questions that are specific to the quiz off the forums. The next quiz, so there'll be a quiz for covering a little bit of today's lecture in prep for Wednesday's lecture. Ideally, I want that in future Mondays to sort of be active as soon as the lecture finishes. Due to other circumstances this week, it might be delayed by a few hours just while I get things sorted. But it should be available either tonight or early tomorrow morning. And then that'll be due again just before the lecture. Just a couple of things on the quiz. Yes, as I said, it's your best 10 out of 16, hopefully 16 quizzes. I plan to have 16 quizzes. So if you have to miss one because you're ill or away, basically I'm not going to be granting any extension for a single quiz. If there's like a reason why you have to miss a whole chunk, then please get in touch. We can sort of talk about your options on that front. The first assignment I will also be making available probably by the end of this week, because it'll be due in 2 weeks' time, or it's due at the end of week 4. And so that'll be covering the material that we cover last week and this week, and a little bit of what we cover next week as well. I also made available a challenge question. I'm not sure what the format of those is going to be going forward. It was a nice question that I could actually rig up the website to actually spit out an answer for you if you haven't have a go. Apparently people were very keen and already, before the day was out, had already seen half a dozen people had made an attempt and also given proofs as to why the answer is what it's supposed to be. I hope I can get a few more challenge questions of that ilk, a little bit more perhaps getting you to practice a bit of programming around some of the topics. As I said, they're purely voluntary. There's no penalty for not doing them. The idea is that it's to push you in, to get you to explore different areas of this course that I'm not covering or don't intend to cover. Part of the way I set up assignments and quizzes is to do that as well. So the quizzes and the assignments will go beyond the lecture material, but it shouldn't be too far beyond. You should be able to get there within 1 or 2 sort of steps. The idea is, again, I'm trying to push you to get you to work with the definitions. So I'm not just after, give me the definition of this. I'm not interested in that. I want to see, how can you actually make use of that definition to solve particular problems. And most of the time, this is my own pet thing I like to do, is just sort of give a quick recap of what we did last week. But more importantly, perhaps for you, is to give a summary of the key things from last week that you should make sure that you take on board going forward, because they're likely the things that I'm going to be assessing looking forward. So just recap of what we covered last week. So on Monday, the main thing I talked about was the idea of proof strategies, how you go about proving particular properties, or ways of going about proving particular properties. And we'll be using that going forward, particularly when it comes to the assignment, when I ask you to prove things. And then on Wednesday, I covered some topics in number theory. We already gave you quite a number of definitions, and today's not going to be any different. Maybe some things you've seen before, maybe some things you haven't. So we had the floor, the ceiling functions, the idea of an interval. So we have the closed intervals and the open intervals. The absolute value function, the divides relation, and some concepts around the divides relation. So we have greatest common divisor, the least common multiple, and then some computer science-based operations, the div and the mod operator, and then the mathematical version of the mod operator, which is the mod n, congruence mod n. So what of those do you actually really need to know? So fundamentally, you do need to know how to present proofs. You'll get practice, as I say, plenty of practice. You'll get some practice to do that. As I said, I'll put up practice problems to give you more practice. Because we don't have tutorials, I'm quite happy to sort of give individual feedback if you're not sure about how your proofs are going. That's what the consultations are for. That's what my the forums are for. That's what my email is for. So certainly, if you're not comfortable with proofs, have a go at practice proofs. Look at the practice problems. Look at the solutions. Solutions to the practice problems will be available too at some point, I think. So you need to know how to present proofs, and then of course with foundational topics like the first few weeks here. What do you need to know for the for the rest of the course? Well, fundamentally, you do need to know everything that was covered, because everything that was covered will come up again and again. So you do. It's good to know it. Now, what do you need to know? Really, the most important thing out of everything we did last week is the idea of the divides relation. Once you're sort of familiar with that and comfortable with that, and then the derived operations that come from it, the greatest common divisor, the least common multiple, right? A lot of the examples that we're going to see in the next couple of weeks will make a lot more sense, because the divides relation gives you it gives me a good example that doesn't conform to what you'd expect. So a lot of definitions have sort of a foundational concept involved. Like, for instance, we talk about ordering. So when we talk about ordering, you're quite familiar with the idea of a less than or equal to or greater than or equal to in your ordering. What you may not be familiar with is that the divides relation can be viewed as a type of ordering, right? And so if you become comfortable with the divides relation, then you can start to see why we can use divides as an example for the notion of ordering that we're going to be talking about next week. And likewise, greatest common divisor and least common multiple form examples for somewhat for other definitions that we make useful. And also the A congruent to B mod n is another example that we will see today, hopefully. So in terms of what's likely to be on the exam, so on and so forth, it's very early days. So really, everything I've covered so far is on the need-to-know basis. So that's what we did last week. So let me just talk briefly about what we're going to do for the next couple of weeks. So for the next 4 lectures, I'm going to talk about sets, relations, and functions. And today is going to be a bit of an introductory lecture. I'm going to introduce sets and relations and functions. So introduce some basic notation and definitions. And then Wednesday, I'm going to talk a little bit more detail about sets and set theory. And then on next week, I'm going to talk about relations. And then on Monday, and then functions on Wednesday. And functions leads me on to the notion of big O notation, asymptotic complexity, which is a topic that is not usually covered by mathematical discrete maths courses. It's usually covered by computer science discrete maths courses like this one. So the various, it does follow more or less the second half of the first chapter of the textbook, but it does touch on some other chapters. And when we talk about some more detailed things, when we talk about relations and when we talk more things in functions, we'll cover some other chapters, which I'll include on the slides for next week. So just sort of give you just a brief rundown of what I'm going to try and talk about today, hopefully. So I'll just start off with, as I've been trying to do, or I'm planning to do this whole semester, give a one slide summary of the applications of this particular topic. And then I'm going to introduce you to sets and to relations and to functions. And one little topic that fits in just before I get to relations is the idea of a formal language, which again is a very computer science oriented topic, but it's a very, very important, from computer science perspective, notion. So what are sets and formal languages and relations and functions useful for in computer science? So, well, sets themselves are the building blocks of just about every mathematical structure. In fact, in the early 20th century, a bunch of mathematicians got together and said, can we define all of mathematics starting from just sets? Right? And so from sets, you define what a number is, and then you define what addition is, and then you define what multiplication is, and so on. And you can build yourself up. And there is a notion of basically formal mathematics based around sets. Like the set is the fundamental object, and then you define all your theorems based on sets, and then 100 pages later you prove that 1 + 1 is equal to 2. This is true. Russell and Whitehead did this, and it's like, I think it was a footnote. They said that this theorem may prove useful in some cases. Anyway, it took them 160 pages, but that's because they had to get all the machinery down to actually define what plus was, what 1 was, what 2 was. Once you've defined all those, actually proving that 1 + 1 is equal to 2 is reasonably easy. Anyway, sets are the building blocks, or one form of building blocks. These days, sort of the modern interpretation, people are looking towards other types of building blocks like category theory. There are other options, but generally sets are considered the basic starting point for all maths. From sets, we define relations and functions, and we'll see how we do that in a bit. But basically, relations and functions are the way mathematicians like to abstract the notion of interactivity. Right? How are two things connected? How are they related? Right? So relation literally comes, is the idea of relating things. But in computer science, we sort of we take those relations. We sort of say, oh yeah, we're interested in modelling real-world problems, and a lot of real-world problems are based on some sort of interactivity. And so things like databases are all heavily reliant on the notion of what a relation is. Right? Basically, a database itself is just a relation. Right? It's a collection of data points that you relate somehow. So, for instance, your student number, your name, the classes you attend, and where you are at 4 o'clock on Monday are all items that are related by the fact that they pertain to yourself, right? This room, this course, this time, right? Those three things are all related by the timetable. Right? So all the databases basically are just collections of relations or relations themselves. Going back to what I was talking about before with the divides relation, right? Any ordering, so you sort of like say, the ranking of students in this class, or the what's another good ordering? Oh, the time of day, how late I'm going to run this course. All those sorts of orderings are relations. So whenever we want to take some data and maybe add an ordering on it, that's imposing a relation between various elements of that relation. Also, in 3 weeks' time, we're going to talk about graph theory, and graphs themselves are also models that model relationship between entities, and so they themselves are relations. Basically, relations are to computer science what sets are to mathematics, right? Relations, I would say, are the building blocks of computer science. And functions are a type of relation. But functions are, almost more computer sciencey than relations are, because every program is a function. Right? A function is just a thing that takes an input and gives you an output, which is precisely what programs are. And in fact, some people go even as far to say is that programming itself is just writing functions, and they call this functional programming, which you may have heard of. But in general, you can sort of look at it a little bit more abstract. Functions, any sort of program can be viewed as a function, something that takes an input and produces an output. And so they're the three cornerstones of the next couple of weeks. But today I'm also going to be talking about formal languages. And formal languages it's a way of describing, formalizing the notion of what we mean by sort of a set of words, a language. And when you talk about, when you do any work on compilers or programming language design or text searching, for instance, all the computational aspects of those things are heavily reliant on the notion of a formal language. And so we'll see that when we get to it in a little bit. But first of all, I'm just going to start with a sort of a slow introduction to sets. I imagine a lot of you have seen sets. I've already been using them fairly informally up to now. I mean, we've already seen some basic sets like the natural numbers, intervals, the real numbers, and so on. So just what exactly is a set? It's a bit hard to nail down what exactly is a set if it's the fundamental object that everything is built on. But from an informal way, a formal viewpoint, we say that a set is just a collection of elements. But there are two things that you can talk about with collections of elements that we may or may not consider. So one is the order of the collection of elements. So if I talk about a collection of elements, I can sort of say, right, I've just got a group of things, and it's like I don't care, A and B and C is the same as C and B and A, right? I don't care. There's no order associated with it. On the other hand, I might be interested in, say, the first thing in my collection, the second thing in my collection, the third thing in my collection. So in the case of sets, there's no concept of a first thing or a second thing or a third thing, right? It's just a collection of things. And the other thing about sets is we don't have multiplicity, right? So if I've got two copies of the same thing in the set, then it's the same as having one copy of that thing in the set, right? So the set containing 1, 1, 1, and 2 is the same as a set containing 1 and 2, right? However, we do distinguish between an element and the set containing the element. So A is an element, whereas curly brackets around the A is a set containing A, and these things are always different, right? An important a particular important set is the empty set, which I will flip. I will use sometimes this. This is not phi. This is O with a slash through it. Right, it's a diagonal slash, or empty braces. Right, so the empty braces notation. It's often I find that a little bit more intuitive to understand. Basically, it's a set that contains nothing. Right. So, for instance, all the integers whose square is 2. Right? That's a set that contains nothing. All the natural numbers that if you add it to 1, you'll get 0. Right? That set is an empty set. Right? Now, I say an empty set. There is only one empty set. There is only one collection of nothing. So all empty sets are the same empty set. So this is an empty set. It has no elements. This set here is not an empty set. Right? This is a set containing the empty set. So we can have sets containing sets, and you can get into some contradictions when you talk about things like the set containing, some sets contain themselves and some sets don't. And we're not going to talk too much about the contradictions. We're going to keep things relatively flat. Right? So we'll talk about maybe sets of sets, but that's about as deep as we go. But this set here is not empty. It has one element. The single element it has is the empty set. Right? It might be easier to comprehend if I wrote it like this. Right? It's the set containing the empty set. Right? So remember, this is the empty set. This is the set containing the empty set. Always the case that A is not equal to the set containing A. So as I said, there's only one empty set. There's only one set containing A, right? For if you have an A, right? There's only one set that contains A. There's only one set of natural numbers, right? So we equate sets by looking at their elements. We say, right, this set is equal to this set if they have the same elements in them. How do we define sets, or how do we describe sets? There are three main approaches that we use. The first one works quite well for finite sets. So finite sets only has, a fixed number of elements, and that's just to list all the elements in there. Or maybe, if it's clear what the pattern is, we might do a ... But for instance, so the set containing A, B, and C. And now this is where I talk about duplication and order doesn't matter, right? So the set containing A, B, C is the same as the set containing A and B and B and B and C. And that's the same as the set containing B, C, and A, right? Those sets are all the same. And all sets contain 3 elements, A, B, and C. All right? Another set here, right? These are all sets with all their elements listed, right? This set here contains 2 elements, A and a set containing A. Right? And here, this set contains 3 elements, A, a B, and a set containing AB. S4 is the empty set. S5 is not the same as this set here. Right? S5 is the set that contains this set. So it still only has one element, right? So basically, this is its one element. Right? And S6 is a set that contains 2 elements. Right? If I call this set A, right? So S5 is the set. So I'll call that set A. Right? S5 was the set containing A, and S6 is the set containing A and the empty set. Right? I think it's a little bit easier to understand what's going on if you pull away from the parentheses, from the bracketing. Right? If you look at the bracketing, it's a little bit complicated to see what's going on. But if you start using symbols for your sets, it's very easy to see that S6 should have, well, as long as A is not equal to the empty set, S6 has 2 elements. That should be very apparent there. And S5 has one element. That should also be apparent. So that's one way to define sets. A second way is to start with, say, some sort of universal set and throw some things away. Right? So that's what's called taking a subset. And there are a number of ways we do that. We've already seen one, that's taking an interval. Right? So for instance, the interval 1, 5 as a subset of the a subset of the integers is just the set 1, 2, 3, 4, 5. Right? It's a set of things that are greater than or equal to 1 and less than or equal to 5 that are integers. Right? So it's 1, 2, 3, 4, 5. If this was reals, I wouldn't be able to explicitly list all the elements like that. Instead, we turn to maybe what's known as a set comprehension description. So take the set X, where X is a member of the universal set, and there's some condition on X. So we call it a logical property, P of X, a proposition that depends on X. Right? It's something that when I give it an X, it becomes either true or false. Right? So P of X, X is even, is an example of a proposition. Right? So P of 2 is true, P of 3 is false, for example. And so the set X, where X is a natural number and X is even, is just the set 0, 2, 4, 6, 8, just the even integers, the even natural numbers. We can also play around a little bit with notation when it's sometimes useful, and the book does this. I don't think I do it much in the slides, but just in case I do, this is what I mean by it. For instance, if you take the integers, and so twice the integers is just the set of integers, or 2x, where x is an integer, right? So this is all the integers multiplied by 2, the set of everything in the integers which is multiplied by 2. And we can extend it to also addition, so 3z plus 1 is an abuse of notation to mean the set 3x plus 1 where x is an integer, right? So it's 1, 4, 7, 10, minus 2, minus 5, so on. So all the things that are congruent to 1 mod 3, if you like. So that's the three main ways we go about sort of taking a subset. And then the third, just a note on subsets. So notation, we use something that is called subset, the subset sign, which is a subset and a line underneath it, to say that S is a subset of T, and this includes the possibility that S is equal to T. Right? So this just means that S is a subset or equal to T, if you like. If I drop the line, it means that S is a proper subset. That means it's not equal to. So it's a subset and S is not equal to T. The empty set is a subset of all sets. Right? S is a subset if every element in S is an element of T. So there are no elements in empty sets, so every element in the empty set is an element of S for any set because there are no elements in the empty set. Right? So the empty set is a subset of every set. For the sets we've already seen before, so the positive integers, the positive natural numbers, are contained in the natural numbers, contained and not equal to, because 0 is in this set but not in this set. Right? And the natural numbers are contained but not equal to the integers, because, say, minus 1 is in this set but not in this set. And they are contained in the rationals, because a half is in the rational, but half is a rational but not an integer. And they themselves are contained in the reals, because pi is a real number but not a rational number. Right? So there we have proper containment between all the sets we've seen before. And so a bit on notation, just so this is the symbol for element of. This says that A is an element of this set, so it belongs to this set here. and this is the subset. Right, so element of E, subset looks like a C, underline C. Looks like a bit of an S if you were to curl through. So A is an element of the set AB. A is not contained in the set AB, right? Because containment relates sets. Right? The set containing A is a subset of that. The set containing A is not an element of AB. Right? So just sort of like that's something that people can occasionally get a little bit tripped over, right? But basically, element of is for elements, subset is for sets. Anyway, the third way of defining sets is by building up from pre-existing sets. So we've already defined a few sets, like the natural numbers, intervals of the natural numbers, the empty set, and so on. And then we have these 5 basic set operations, they're known as. Union, intersection, and complement are the sort of the 3 main ones. And then 2 more derived ones. These are, you can define these set difference and symmetric difference in terms of the other 3. These are sort of the basic set operations, and we're going to talk a lot about them today and again on Wednesday. So that's one construction, is to build them up using these operations. Another construction is to take the power set. Right, so the power set of a set is the set of all subsets. So as an example, right, if my set was, I think this might even be an exercise. My set is AB, right? So it's my set. The power set of A, right? The set of all subsets of AB. So empty set, yep. Empty set is a subset of all sets. The set containing A, the set containing B, and the set containing A and B itself. Right, so this is the power set of A is a set of sets. And the last construction, which I'll talk about right at the end of the topic on sets, is the Cartesian product. Right, and that's sort of the way of making your sets go in more than one dimension. It makes sense. That'll make sense in a little bit. But first of all, I'm just going to talk about, just define the set operations. So if you're not familiar with these things, they can get a little bit confusing, but basically union and intersection, union and intersection, so union and n. The union represents OR, right? So the union of A and B is the set of things which are in A or in B, or both, right? Whenever we say OR in mathematics, we mean inclusive OR, right? So or both, unless we explicitly say no, it's exclusive. The intersection, so where the 2 sets intersect, is the same as AND, right? It's A intersect B is the set of all things which are in A and in B. And then the last basic operation is complement, so A complement, and this usually has to be with respect to some sort of universal set, right? So it's because it's like, I can't just talk about the complement of the set of forks, right? What does that mean? Is it the set of all cutlery items that aren't forks, or is it the set of everything? Am I in the complement of the set of forks? So you have to have some sort of universal set that you're talking about. And so the complement is the set of all things which are in the universal set, but not in, the complement of A, not in A. And one quick little side definition that I'm not sure if it comes up. It will certainly come up at the end of when we start talking about probability, is the notion of disjoint. So two sets are disjoint if their intersection is empty. So they're the three main things. You will get familiar with union, intersection, complement. I'll give it a visual interpretation of them in a sec. But the other two set operations that I defined or mentioned earlier were set difference. So A without B, A minus B. I always say without A without B is the set of things that are in A that are not in B. Right? And it's also defined as the intersection of A with the complement of B. Right, so it's a set of things that are in A and not in B. And then the symmetric difference, which is nice, one that crops up in computer science quite a bit, because it's basically the exclusive OR. Right? So it's the things that are in A or B, but not both. Alternatively, A and not B, or B and not A. Right? And so this is defined as A without B, union B without A. So given that we've defined set minus, set difference in terms of intersection and complement, you can turn this into definitions in terms of intersection and complement. So I've been talking a little bit like sort of A or B, A and B. There is a correspondence between set operations and logical operators. Some people have already brought it up when talking about some of the propositions that we talked about on last week. They've sort of got in their mind, I mentioned it myself, you talk about the set of worlds where this proposition is true, right? And the set of worlds where that proposition is true. And so the union of those sets of worlds is the set of worlds where one or the other is true. Anyway, we'll see this correspondence when we talk more about logical operators, and a little bit more on Wednesday when I talk about set theory in more details. But a nice connection between intersection union and the subset relation is that you can define subset in terms of, say, intersection or union and equality, right? So if A union B is equal to B, then A is a subset of B. Right? Likewise, if A intersect B is equal to A, then A is a subset of B. And this is two-way implication. So IFF means if and only if. I don't think I mentioned that last week. So, all right. So I've already done the first exercise, but I'll freeze that, and I'll just go back up to the definitions of set difference over there. Right. So the problem is A symmetric difference with A, and A symmetric difference with the empty set. So just to sort of get you familiar with things, I'll give you a quick minute to think about it. So the symmetric difference of A with itself is empty set, right? So this is the set of things which are in A but not in A, right? Or in A and not in A. So there's nothing that's both in A and not in A at the same time. So it's just the empty set. And if I take the symmetric difference with the empty set, it's A, yeah. So there's a set of things which are in A but not in the empty set. Well, that's just everything that's in A, because everything that's in A is not in the empty set. and everything that's in the empty set. Well, there's nothing in the empty set. Right. So two nice results, which we may come back to in a little bit. Right. So the power set of AB was, as before, the empty set, the set containing A, the set containing B, and the set containing AB. This, if you're familiar with working in Mod 2, this might give you an idea why we use the symbol plus, right? So 1 plus 1 is equal to 0. 1 plus 0 is equal to 1. But again, we'll touch on that a little bit more when we talk about logic. Cardinality. So the other thing we can do with sets is count the number of elements in them. So there's a number of notations. This one is apparently the default set in my macros, which is annoying because that's also the one for absolute value. But there is a connection I'm not going to talk about too much. But basically, so we talk about the number of elements in a set. The context should be clear whether we're talking about the cardinality or the absolute value. But the number of elements, that's also written as sort of like, I say hash or pound or octothorpe x, or card x when basically you don't have enough symbols and you only want to listen. But basically, cardinality is the number of elements in the set. And for a finite set x, the number of elements in the power set of x is always 2 to the number of elements in the set of x. Right? So before we saw my set AB, right, contains 2 elements. The power set of that contained 4 elements. 2 to the power 2 is 4. Right, so some more lengthy set of exercises, just to because these make nice multiple choice type questions. Just to sort of like run through. So, what's the cardinality of the empty set? 0. Right? Cardinality is the number of elements. There are no elements in the empty set. What's the power set of the empty set? Good. It's not got quite a few answers. Right. Right. So remember that the power set of a set is the set of all subsets of that set. Right. So, the empty set is a subset of the empty set. So that's included in there. There's nothing else. Right, so now we have the set containing the empty set, which is not the same as the empty set. Right, this is not the same as the empty set. And so the power set is the set containing the empty set, and so it has, as we discussed right at the start, 1 element. Just leave that in there. Yep. What about the power set of the empty set? 1. What do you mean 1? One's not a set. Well, yeah. So if I call this A, like I did before, the power set of A is the set of all subsets of A, right? The empty set is a subset of A. It's also an element of A, right? It's both. Right, this is a special case. Generally, you can't assume, you're going to have one or the other, but in this case, we actually have both. The empty set is a subset of this thing, and it's also an element. So it's a subset, so it's an element of the power set. But also, A itself is a subset of A. And as we discussed before, A is not equal to the empty set. Right, so the power set of A consists of the empty set and A. Right, whenever you're doing the power set of something or other, always start with the empty set. Right? The empty set is always an element of the power set. Right, so the power set of A, which is the power set of the empty set, is the set containing the empty set and the set containing itself. And it has two elements. The size of the set containing just A, right? There's only one element in A, so it has 1. The power set of A, empty set and A itself, so it has 2 elements. Okay, what's the cardinality? So assuming this is an interval of integers, what's the cardinality of the closed interval from m to n? Let's just assume that n is larger than m. Right? If n is smaller than m, then it's the empty set, and so it has 0. N minus m plus 1. Okay, do people see why? This is just m plus 1, m plus 2, right? Whatever this is here, up to n. Right? So if I count them all up there, well, what is this? This is m minus n. So it's going to be n minus, or m plus n minus m. Right? So how many elements have I got? I've got 1, 2, 3, 4, up to n minus m plus 1. Sorry. Let me write that up better. Okay, so mn is m plus 1, m plus 2, up to n. But if I want to write n as m plus something or other, this is m plus, what is it, n minus m. Right, so if I write it like this, I can see that I can count. It's easier to count up the number of elements there. There's 1, 2, 3, 4, n minus m, plus this one that I forgot to count at the start. So I get n minus m plus 1 elements.
What if the universal set is real numbers?
If the universal set is the real numbers, then then this thing here. So if I'm talking about a subset of the reals, then if m is not equal to n, if m is strictly less than n, right? Then how many elements? Infinity. If m is equal to n, if m is greater than n, empty, so it's 0. Yeah, I'm counting the number of elements. So as far as we're concerned, it's just infinite, right? You can go into, there's more mathematical concepts of defining different types of infinity, right? So you can talk about a countable number of infinities versus an uncountable number of infinities. I'm not going to do that. That requires stuff beyond the scope of this course. However, I'm happy to answer any questions about that. But because we're computer science, we like to deal with things in the finite. Basically, as soon as it's not finite, it's infinite, and we don't care. Nope. So n minus m plus 1. All right. Now we'll go to an exercise from the book. This is quite a nice exercise. It highlights a few things. So I'll give you a few minutes to come up with some numbers and throw them at me. And meanwhile, I can answer any questions anyone has about anything else for the time being. I should say that these intervals are assumed to be intervals over the integers or natural numbers. Okay. So for the first set, right? Well, there are so n in 1 to 4 means that n takes 4 different values. So this set has 4 elements, right? No. Huh? No, so these intervals are taken to be integers, intervals of the integers. Yep. Right. So, well, let's plug in the values for n. N equals 1, I get 1 over 1. N equals 2, I get 1 over 2. N over 3, I get 1 over 3. Right. So this set is this, and there are four elements in there. N in 0 to 4, there's 5 values that n can take. So this set has 5 elements, right? No? Okay. Right. So exactly. It's not the case. Why not? Well, let's have a look at the values as we plug n into this thing. So if we plug n equal to 0 in here, we get 0. When we plug n equal 1 in here, we get 0 again. Right? When we plug n equal to 2 in there, we get 2. When I plug n equal 3 in there, I get 6. And when I plug n equal 4 in there, I get 12. Right? So although I get 5 values, 5 possible n's, I only have 4 different values. Sets don't have duplication, so there are only 4 elements in this set. So you can't just go, oh, that's 5 things n there, and go like that, right? So what I did in the first case was a little bit cheating. It was a lot of bit cheating, actually, right? You have to actually physically check to make sure that you don't have any duplications going on there. Okay, so here we've got quite a bit of a guard, right? So this is the guard is what's after the colon. This is the things that n has to satisfy. So n has to be a positive natural number. 2 has to divide n, and n has to be less than 11. So there's not a lot of n's that satisfy this. In fact, all we can say is that n has to be an element of 2, 4, 6, 8, or 10. Right, so n has to be an element of those things. 1 over n squared. Right, so this set is 1 over n squared, where n is one of those things there. Right, this is a perfectly acceptable set comprehension. You can write it like this. So what is this? This is just 1 over 4, 1 over 16, 1 over 36, 1 over 64, and 1 over 100, which are, thankfully, all distinct. And so there are 1, 2, 3, 4, 5 elements in there. So this is 4, this is 4, this is 5. All right. Again here, right, I've got infinite possible values for n. Right? But if we look at this, right, when n is odd, we get 1, and when n is even, we get 3. And that's it. Right, so this set here, right, although n can go from 0, 1, 2, 3, right, when n is 0, this is 1. When n is 1, this is, when n is 0, this is 3. When n is 1, this is 1. When n is 2, this is 3. 1, 3, 1, and so on and so forth. Right, it's only ever 3 or 1. So this is just the set containing 1 and 3, so it has 2 elements. Okay, so as I said, a nice question because it highlights some pitfalls that people can tend to fall into. So 4, 4, 5, and 2. So some of you, I know I did it in high school, may have come across Venn diagrams. So Venn diagrams are a way of visualizing sets. The idea being that we have a set here, we have a box here. The box represents the universal set. This represents all the elements that we can possibly talk about. And circles represent particular sets. So if I talk about the set A, represents all the things that are inside that circle. The circle B represents all the things that are inside that circle. The set C represents all the things inside that circle. And Venn diagrams are generally designed so that you have all the possible permutations that you can imagine, right? So it's like here I have this setup with 3 sets here, right? An element in this part of the region is an element that's in C but not in A or B, right? An element that's in this part of the region is an element that's in A and B and C. Sorry, thank you. Let's start that again. Right, just on green. An element in this part of the section is an element that's in C but not in A or B. Element here is an element that's in A and B and C. Right, here's an element that's in A and B but not in C. Right, so you can talk about you could talk about things like, say, A intersect B. Right, that's the set of all things that are in A and B. Visually, this is this region here. Right? You can talk about, say, A intersect B without C. Right? So that's a set of things that are in A and B but not in C. Visually, that's this region here. So things get a bit messy, particularly when you can't distinguish red and green easily. So this is, I'm going to deviate from previous years. This is just a tool to help you visualize things. This should not be used as an argument to establish any results about sets. So what do I mean by that? Well, if we look at the result we had before, A plus A is equal to the empty set. What is, well, visually, what is A plus B? Right? A plus B, that's a set of things that are in A or B but not both. So it's visually it's this set here. Right? A set of things that are in A or B. There's A, there's B, but not both. Right? So we can see that if A and B overlap, if A is equal to B or B is equal to A, basically this overlap is going to take everything. So it's like if A is going to overlap, we're going to have A plus A is going to be the shaded region, right? But there's no shaded region because all my overlap is not shaded. And so this thing here is equal to the empty set. It's a little bit tricky to see on this particular example for A plus A. But there are some ones that you can use to sort of like say show, for instance, well here's a better example perhaps. A without B intersects C is equal to A without B. Is this right? I don't even know. Hang on. Intersect A without C. I hope this is right. Well. Set it as a task. Is this true? Is this result true? Right? Let's visually draw out what A without B intersects C is. So B intersects C is this red area. So that's B intersects C. And then so A without B intersects C is the green area, right, which is everything in A except for that little wedge of red. Meanwhile, A without B is this bit, blue, and let's do it in red. A without C is the red bit. That bit. Okay, not quite. If I just change it to union. And then we see that if I take the union of the red and the blue area, I get the same as the green area. So this is correct by diagram. Right? Now, the problem is, you saw the process I went through to actually generate the areas. And in this case, it's okay. It's easy enough to see what, I've said, like, this is the blue area is the A without B, and the red area is the A without C, and the green area is this, and the red area is that, right? So in this case, it is easy enough to see how these two things become the same, how these two things are equal. In general, however, though, you need this extra time dimension. Is you need to see how these sets are formed, which when you're giving a proof, you don't have available to you unless you're actually presenting said proof. Right? So it can get a little tricky. So I'm going to say just for this course, please try and keep your proofs for algebraic properties of sets, which is what we're going to talk about a little bit next, or quite a lot next time, to using the algebraic laws and just use the Venn diagrams as a tool to help you see what's going on. Right? So it's like if I ask you, is this equal to this, and if I'd had intersection there, you sit there and you can come in and you say, no, they're not. Right? If I had intersection, right? Why isn't the intersection of these two things equal to this thing here? Well, I can see that the intersection there is going to be just this area in here. Right? So, for instance, an element there is going to be in the green one, but not in the black one. Right? And so then my argument to show that this is not equal to the intersection of those two things is to take something that's in A and B, but not C. I take an element X in A and B, but not C. Right? And that element X should be in my green one, but not in my black one, after you do some manipulation. But that's how the visualization tool works, how it works as a visualization tool. So use Venn diagrams, particularly if you're familiar with them, to help you understand the concepts, to help you get the visualization, appreciation of what's going on. When we talk about a subset, for instance, that's a subset of, black is a subset of white there, right? We will revisit this visualization when we talk about probability in a few weeks. I may use the visualization to help highlight some key issues, but in general, I think getting a sensible argument through just from diagrams is just that little bit tricky, and I have in the past allowed it, but I'm based on how unhappy I'm generally am with the results. I think I'm not going to allow it this time.
So we can use Venn diagrams as a tool?
No, you can't use Venn diagrams in submissions to me.
Oh.
Right? You can use them to convince yourself that the argument is going the right way. So it's like, so you can imagine that a question might be something like, is A without B and C equal to A without B intersection A without C, right? So now I'm doing the intersection here. Right? So this would be the question that would be set on the exam, maybe, something like this, right? And it's like, the answer is yes. Then I'll say something, if the answer is yes, prove it. If no, give a counterexample. Right? And I should mention, is this for all sets A, B, C? Right? I'll try and remember to put that in, but it's like generally if you write something like this, there's an implicit. Is this the case for all sets A, B, and C? Right? So if yes, prove it. If no, give a counterexample. So you've got to give. So in this case, we know it's not the case. You've got to give a counterexample. You have to give me concrete sets A, B, and C, where this and this are not going to be the same thing, right? So a particular example might be sort of like A is equal to 1, B is equal to 1, and C is equal to the empty set. And I think that should serve as a counterexample, I believe. Yes. No. No, it won't. Oh, well. Nah. Well, anyway. I don't know, right? So, I'll just put it quick. I'll leave it as an exercise. Right? This is the kind of question I like to ask. Right? Because it's like, I'm not asking you to give me the definition of intersection. I'm not asking you to give me the definition of set difference. You need to know those in order to understand the question. Right? So this is the question. You get phrased with this. I'm not telling you which direction to go. You need to decide for yourself which way to go. So this is where you can use Venn diagrams. Use Venn diagrams to make the decision. Right? Draw a picture, color things in. That's fine because you yourself are seeing the process, how it's going on. At the end of the day, your rough work is going to look something like this, right? And it's almost indecipherable at looking at the final product, what the process is to get there. And that's what I'm interested in. I'm interested in the process, which is why you have to give three concrete sets, A, B, and C, where A without B intersects C. So you do the computation. So A without B intersects C would give me something like 1, 2 without the empty set, which is equal to 1, 2, right? Meanwhile, A without B is equal to 2. A without C is equal to 1, 2. And the intersection of those two things, intersect A without C, is equal to 2, which is not equal to 1, 2, and so they're different. Hey, so there's a proof that they are different. But that's the point. I'm interested in the process more than the final result. Anyway, so use Venn diagrams to help you understand concepts. Don't use them in proofs. Please, for me. Other mileage may vary. But they're very useful for answering a question like this, which I'm now not going to answer directly. I'm not going to leave it for you guys to do. Relating the cardinalities of A union B, A intersect B, A without B, A symmetric difference with B, and A and B. Right? So here's my A, here's my B, right? So importantly, if we look at, say, A union B, right, and I want to count the number of elements in that, right, well, what I can do is I can count the number of elements in A, I can count the number of elements in B, and, well, what have I done? I've counted the number of elements in here twice. So I need to subtract out the number of elements in the intersection. Right? So this is what's known as inclusion-exclusion. I think we touch on that again later on. But you can rearrange this to sort of say, right, A union B plus A intersect B is equal to A plus B. Right, so there's a relation between the size of the union, the size of the intersection, and the size of A and B themselves. What about A without B? Right, well, that's just the red area here, right, which is just the elements of A minus the elements in the intersection. And what about the symmetric difference? Right. Well, that's just the new red area. Right. So what is that? Well, that's just the size of the union minus the size of the intersection. Right. The size of the union was the whole lot minus the blue bit. Right. But of course, I can write the union in terms of those things there, so I get this is the size of A plus the size of B minus 2 lots of the intersection. Right, so if you like, this is A or B but not both. Right, so I count all the things that are in A, count all the things that are in B. Now I've counted all the things that are in both twice. So I need to count all the things, I need to remove all the things that are in both 2 times. That brings me to the last set construction, which is very important for the next section, talking about formal languages, and that's the Cartesian product. Now the Cartesian product, so if you take 2 sets S and T, the Cartesian product is basically you take a set of ordered pairs. So with sets, order didn't matter. With ordered pairs, order does matter, right? The ordered pair 0, 1 is different from the ordered pair 1, 0. So the set of ordered pairs where the first element comes from S and the second element comes from T. And this is just the Cartesian product S times T. This notation here is a little bit clunky. That's just a big multiplication sign. So you may be familiar with summation signs. You may have seen this idea of, so instead of writing 1 plus 2 plus 3 plus ... you write it as the sum of, as I goes from 1 to n of I. Like that, maybe, hopefully. Right? This notation here on the slide, right, times SI, I goes from 1 to n, is just shorthand for S1 times S2 times S3 times times Sn. Right, so it's a big times. The reason why I do it like this, or you present it like this, is because I want to have not ordered pairs, but ordered tuples. So ordered sequences of n things. So that's if we've got n different sets SI. If all the SI are the same, which happens quite a lot, so S times S we often abbreviate as S squared, or S times S is S cubed. In general, S times S n times we write as S to the n. Some quick observations. The empty set times S is always equal to the empty set. Why is that? Right? Well, remember, empty set, or S times T, is the set of ordered pairs where S comes from S and T comes from T. So this is the set of ordered pairs where the first thing comes from here and the second thing comes from here. Well, there's nothing in here. So the whole set has got no elements in it, so it must be the empty set. This is quite an interesting concept when you start to talk about infinite products, which I'm not going to, but you can actually have infinite products where you think it should be empty and it's not. That's just playing around with strange definitions. In general, the cardinality of S times T is the cardinality of S times the cardinality of T, hence the notation. And if we talk about the product, the SI, this is a fancy product, fancy multiplication. So think of it like the sigma that I just wrote. This is for times, which just says S1 times S2 times S3 times. This will become important when we talk about combinatorics in week 7 or 8, whenever that is. But some examples just to see how it works. So A is the set 0, 1, and B is the set AB. Right? A cross B is the set of ordered pairs where the first thing is from A and the second thing is from B. Right? So it's 0A, 0B, 1A, 1B. Now, I could also, because sets can be in any order, right? So this is the same as 0A, 1A, 0B, 1B, right? These are the same elements in different order. If I do B cross A, the first thing is from B, the second thing is from A, right? So it's A0, B0, A1, B1. This is not the same as this set here, right? A0 is not the same as 0A. 0A is the same as 0A, 1A is the same as 1A, 0B, right? So all these match up, but B0 isn't in this list. A0 isn't in this list, right? If B had been 0, 1, then yes, they would match up. A squared, set of pairs, 0, 0, 0, 1, 1, 0, 1, 1. A cubed, the set of triples, right? 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Right? Order, for tuples, for ordered pairs and triples, order matters, duplication matters. Right? 0, 0, 1 is different from 0, 1, 0. Right? And it's a triple, it's three things. There's two zeros and a 1. So that's the introduction to sets. On Wednesday, I'm based looking at the time. I may not get through all these topics today. On Wednesday, I'm going to talk a little bit more about set theory, right? And that's about establishing results like the one that I was talking about before, right? How do we go about, so in this case the answer was no, but if the answer was yes, what do I mean by prove it? How do I actually do that? We can't use Venn diagrams, what do we do? Right? And the answer is that we use set theory, right, which basically is just a bunch of rules which tells us how to go to show that two sets are equal. Anyway. So now I'm just going to talk a little bit about formal languages. So formal languages are basically the idea of what would happen if you took a mathematician and asked them to study language. Right? So first of all, they say, right, well, what is English? English is just made up of words. And what's a word? A word is made up of letters. So let's start with that, right? So we'll start with what we call an alphabet, which we pretty much always denote by sigma, capital sigma. We call it an alphabet. It's a finite set, and it has elements. Right? So alphabets are not much use if there's no symbols in it. Elements of the alphabet are called symbols. So typical examples of alphabets, right? The alphabet for English words, right, is just the set of letters A, B, C up to Z. If you want to do some fancy things, maybe hyphenated words, maybe put some spaces in, right? Binary integers made up of zeros and ones. Decimal integers made up of 0, 1 to 9, right? All these alphabets have a natural ordering, like A is less than B, and B is less, so you can talk about, say, 0 is less than 1, and so on and so forth. But that's not a requirement as part of an alphabet, right? And in this case, something like the set of all Chinese characters is an alphabet, right? Subject to the assumption that there's only a finite number of them, right? The set of keywords in a programming language is a finite set of alphabet. So now we've got an alphabet. Well, a word is just a string of symbols from your alphabet. And it's a finite string. We only talk about finite words. So a finite string is just like a sequence of symbols from sigma. So sequence, order matters, duplication matters. It's just like when we talk about the Cartesian product, right? We talk about tuples. Exactly, there's an exact correspondence with words. Words can be thought of as tuples. A very important word is the empty word, which we denote by lambda. This is the word with no symbols. Right? So it might seem strange. It's like, why would we like, what's the point of having a word with no symbols in it? It's the same reason we like to have the empty set. It actually forms the basis for everything. This can form the base case for a lot of things. So we reduce everything down to the empty word. We reduce everything down to the empty set. Right? That can often form a base case for things like inductive proofs. So the empty word is very useful. We denote it with lambda. Some courses denote it with epsilon. I'm just following the syntax of the book. So example of words. So the word ABA, right, is a word over the alphabet of A and B. 0, 1, 1, 0, 1, 1, 1, 1, 1 is a word over the alphabet 0, 1. Importantly, it has to be finite. This dot, dot, dot is sort of just meaning like some number of ones. An important function about words is the length, which is just the number of symbols in the word. So for instance, the length of AAA is 3. The length of the empty word is 0. There are no symbols in the empty word. And really the only thing you can do with words is concatenate them. Right? And we do that by just sticking them next to each other. Right? So you have the word cat and the word dog, you concatenate them, you get the word cat dog. Right? Or the word catenation, the word con, you put them together, you get catenation con. Right? Order matters with concatenation. Right? If I put one word before the other versus one word the other way around, I could get completely different words. So usually I use V and W to represent words, A and B to represent symbols if we're going to letters, or 0 and 1. So the front of the alphabet is symbols, the back of the alphabet is for words, just to try not to confuse things. If we concatenate the empty word to a word, right, it's the same as just the word itself. Right? The concatenation is the empty word followed by a word is just the word itself. Right? The empty word adds nothing. So we can concatenate the empty word as many times as we like, and we still have the same word. And the length operator, the way the length operator works with regards to concatenation, the length of the concatenation of V and W is equal to the sum of the lengths of V and W. So some examples. So if W is the word ABB, V is the word AB, and U is the word BA, then say the word VW is the word, so take V, which is AB, concatenate it with W, which is ABB, and I get AB, ABB. WW, right, is ABB, ABB, but VUBB, right, V is AB, U is BA, so VU is ABBA, followed by BB, ABB, ABB, right? So WW and VUBB are the same words, right? So even though I would think of WW as ABB, ABB, and VUBB as ABB, ABB, right? The pauses are just my taking of it. When we concatenate things, we just throw away the spaces. We throw away the differences. The concatenation of W, lambda, and V is just the same as W followed by V, which is ABB, AB. The length of WV, right? Length, remember, is the number of symbols. W and V are not symbols. W and V are words. Right, so VW is ABB, AB, which has 5 symbols in it. So the length of VW is not 2, it's 5. So that's what a word is, concatenation. Finally, so a word is a string of symbols, and a language is a set of words. So first of all, just some definitions. So sigma to the k, right? Well, sigma is a set, remember? Sigma is a finite set. Sigma to the k we defined before was a set of all, it was like sigma times sigma times sigma times sigma, right? Set of all k tuples. We can also view k tuples as a word of length k, right? Order matters, duplication matters. So although this looks like it might be in conflict with the notion of Cartesian product, it's not. They really are the same thing. And they can really be seen as the same thing. So sigma to the k is a set of all words of length k. Sigma to the 0 is just The set of words of length 0, there's only one of those, that's the empty word. Right, so sigma to 0 is the set containing the empty word. And sigma to the 1 is just the set of all symbols in sigma, so all words of length 1. Then sigma star is the set of all words of all finite lengths. So we don't have any infinite length words in there, but the set sigma star is in general infinite in size. Right? There are arbitrarily long words. There's just no infinite words. So there's a slight difference that people also tend to get a bit confused on. So sigma star is a set of all words. Sigma plus is just the set of all words apart from the empty word. Another way of writing sigma star is that sigma 0, union sigma 1, union sigma 2, union sigma 3, so on and so forth. Or the union of sigma to the I as I goes from 0 to infinity, or so the limit. So this is this, sorry. This here is the set of all words of length at most n. And a language, so sigma to the star is the set of all, so sigma star is the set of all words. So a language is just a subset of sigma star. It's a set of words. And generally, we are mostly interested in subsets that can be described according to certain rules. Because in general, languages have infinitely many words. Right? No, there's no infinite word in a language, but there may be arbitrarily large words. And so generally, we're interested in languages that can be defined in terms of certain rules. And those rules are what are generally known as a grammar. I'm not going to talk too much about grammars here. For those of you that may be familiar with like regular expressions, you might be familiar with the idea of, particularly when using wildcards in Windows or Unix, right? Star meaning 0 or more, plus meaning 1 or more occurrences. It's exactly the same principle. So a couple of examples of languages. So the language of decimal numbers to 2 decimal places. All right. So the set of symbols that we care about, minus, decimal point, and then the digits 0 through 9. And we take all the words which satisfy the following rules. It contains at most one instance of the minus sign, and if it has a minus sign, it's right at the beginning. It has at most one decimal point, and if it has one, then it has at least one digit before it and either 1 or 2 symbols after it. And then finally, W contains at least one symbol from 0, 1 up to 9. So according to those rules, so 123 satisfies those rules, 123.0 satisfies those rules, and 123.00 satisfies those rules. Right? So those are all words in this language. And because of the way we talk about, words are only equal if we match the symbols. So these are all different words. So that might give an inkling to the opinion I have about whether 6 times 4 and 4 times 6 are the same. That's my opinion, again, as I say, it's only an opinion thing. But right, to me, 123, 123.0, 123.00 are different. It's only when we say, what does 123 mean? What does 123.0 mean? What does 123.00 mean? That we give them a sense of sameness. Another example of a language, HTML documents, loosely. Right? Our symbols now are tags, HTML tags, and the language of valid HTML documents can be loosely described as words that look like the following. They start with this tag, then the next tag is this, then they have some 0 or more symbols from what are known as head items, which we define somewhere else, followed by a slash head, followed by a body tag, followed by body items, followed by a slash body, followed by a slash HTML, right? So we've described a sequence of symbols right? With some hand waving bits, like we've got this and then this and then zero or more of these things and then this and then this and then zero or more of these things and then this and then this, right? So it's a word I've described a set of words, so I've described a language. Right? Likewise, C, Java, all of these, all your favorite programming languages can be boiled down to being described in this way, right? As a language of symbols, right? Where the symbols are things like your keywords, or perhaps more detailed descriptions on coming up with an identifier and things like that. So that's why formal languages crop up all the time when we're talking about compilers, when we're talking about programming language design. Right? It's actually the formal definition of a programming language is defined in terms of formal languages. So I'm not going to talk too much over these exercises. I'm going to try and push through a little bit. So sigma star, as I said, right, if sigma has any elements at all, if sigma has any sigma has non-elements. Sigma star is infinite in size. But if I can talk about the length of words of length at most 4, right? I can look at all the words of length 0, all the words of length 1, all the words of length 2, length 3, length 4, right? Which is 1 plus 3 plus 9 plus 27 plus 81, right? If you don't know your sum of geometric series, don't worry too much about this. This will come up again later on. But fundamentally, if you add up 1 plus 3 plus 9 plus 27 plus 81, you get 121. So there are 121 words of length at most 4 from over an alphabet of 3 letters. Languages are sets, so you can union them, you can intersect them, you can take set difference, symmetric difference to build new languages. But there are 2 operations that you can do to languages uniquely. You can concatenate, so if X and Y are languages, I can talk about the language which is the concatenation of those 2 things, which is a bit like the Cartesian product. It's the set of words that start with something in X and finish with something in Y. Right? And then the clean star operation is the set of words that are made up of concatenating 0 or more words in X. So union, together with concatenation and clean star, form what are known as the regular operations. And if you're familiar with regular expressions, or if you've heard of regular expressions, these are the things that regular expressions are precisely the things that you can define using the regular operations. I won't go into too much detail about that. There's some examples of how union, concatenation, and star work. And some interesting edge cases. So in the last, hopefully I can, I'll probably won't get into functions. I'll talk about relations, because these are sort of the next step after sets. So in general, relations and functions are very closely related. They capture the idea, as I said before, of the abstraction idea of how objects are related, or how objects being related, right? And the reason we don't really care about the reason why they are related, right? So they might be related because they influence one another, or they have some common properties, or they they match when some other things happen. From a mathematical point of view, we're not interested in the why they're related. We just say that things are related. And functions are special kinds of relations where we talk about relating inputs to outputs. So things coming in to things going out. The idea that the functions and relations, they generalize or they formalize the concept of interaction. But importantly, when we go mathematics, we can't just sort of talk about interaction of any kinds of objects. What we do is we restrict ourselves to a certain domain of objects. So in the formal definition, so an n-ary relation, so n here is a variable, so we can talk about one-ary relations, we can talk about two-ary relations, three-ary, four-ary. In general, an n-ary relation is a subset of the Cartesian product of n sets. So a one-ary relation is just a set. Right? The most interesting set of relations are binary relations, and we're going to talk a lot about those next week, which are relations between two sets. In general, it's just a subset of the Cartesian product of n sets. So elements of these things are ordered tuples, ordered n tuples. Right? So elements of binary relations are ordered pairs. So elements of ternary relations, three-ary relations, are ordered triples. And so we write them. So we write the elements of a relation either like this, x1 up to as an ordered triple in R, or sometimes we write it like this. Right? We say R of x1, x2, sort of kind of like a functional notation, like a program. Right? Here's my program. R is my program. Here are my inputs: x1, x2, x3 up to xn. Relations are like programs that spit out yes or no, true or false. Right? You plug things in. It's either the things you plug in are either in the relation or they're not in the relation. Right? These things are related or they're not related. For binary relation, we have those two notations plus a third one where we stick the R in between x and y. Right? So a good example of a binary relation that you're familiar with is equality. Right? Two things are either equal or they're not equal. Right? And we stick the equality relation, the relation symbol, in between the x and the y. Other examples of relations that you almost certainly know: inequality, like less than or equal to, greater than or equal to, less than, greater than, not equal to. The divides relation. Right? Two things, x either divides y or x doesn't divide y. It's a yes or no thing. So these things are all binary relations on the same thing. They always relate two things of the same type. Right? Equality relates to numbers, inequality relates to numbers, divides relates to numbers. But relations don't have to relate things of the same type. For instance, element of is a relation between elements and sets of elements. Right? So either x is an element of a set or x is not an element of a set. Subset, superset. Right? These are all relations between sets. And as an example of a non-binary relation, we've got congruence modulo n. Right? So m is congruent to p mod n. This relates m and p and n in some way. Right? To say that 5 is congruent to 10 mod 5 relates 5 and 10 and 5. Or 15 is congruent to 10 mod 5 relates 15 and 10 and 5. Right? 15 and 10 and 5 are in that congruence modulo n relation. I mentioned at the start that relations are heavily tied in with databases. Right? And this is a reasonably concrete example. Right? So you can take your take a database of course enrollments. So you have a bunch of sets. You have a set of students, set of courses, and you have an enrollment relation, right, which relates the students with the courses. Right? I'm going to relate this student to that course if this student is enrolled in that course. So S is related to C if S takes C. Right? So the enrollments is a subset of the product of S and C. Right? So not every student takes every course, but it could be the case that every student takes every course, but in general, it's some proper subset. And sometimes we require some various conditions, like for instance, a person can't be enrolled in all the courses at the same time, or more than 400 people can't be enrolled in a particular course. And so we have various constraints on our relations. A more complicated example, right, the class schedule database. We have a set of courses, set of starting times, a set of lecture rooms, and then the schedule is a relation that relates courses, starting times, and lecture rooms. So course C is at time T in room R. Another, even more complicated, is, say, a relation that relates competitions and results and years and athletes. Right? So the database that stores all the sports statistics is just in itself a relation. So I will, I think, yeah, I will just leave it on, I'll just finish here on defining relations. So relations are sets because they're just subsets of a Cartesian product. So you can define them the same way as you can define sets, right? You can take the union, you can explicitly enumerate all the tuples in them. You can define them in terms of relevant tuples within the entire range. You can sort of say, I'm only interested in the courses that student S is taking. Or you can construct them from other relations using things like union, intersection, complement, and so on and so forth. One special operation that you can do with relations, particularly binary relations, is the notion of a converse, which is basically the reverse operation. So R relates S with T, the converse of R relates T with S. I will come back to this slide later on, but I think this is a good one to list, right? So here are my sets A, B, C, and X. So A is 1, 2, B is 2, 3, C is 3, 4, and X is 1, 2, 3, 4. The divides relation on X can be listed out like this, right? Because 1 divides 1, 1 divides 2, 1 divides 3, 1 divides 4, 2 divides 2, 2 divides 4, 3 divides 3, and 4 divides 4. Right? The element relation, 1 is an element of A, 2 is an element of A, 2 is an element of B, 3 is an element of B, 3 is an element of C, and 4 is an element of C even. The converse of the subset relation, right? A is a subset of A is a subset of X, B is a subset of B, B is a subset of X, X is a subset of X. And then this is the pre-image, all the things which 2 is less than on X, right, is set 3, 4. I'll come back to those. So, as I said, the quiz for today will appear in a few hours, hopefully, not before tomorrow morning.
Why is the PhD material is different from yours? I mean, the PDF I download from the website is different from
Yep.
yours.
I don't have the, so I hide the answers to the exact exercises to actually give you something to. When I get back, when I get onto a computer, I'll update the slides.
So the week one's material is still no with
Shouldn't, no, week 1 material should be okay.
Okay, thank you.
Hang on.